It's great to be here. It's great to, I think it's the first time in my career that I speak in front of a room almost full of mathematicians. But it's fantastic to be here. What I wanted to do is talk a little bit about problems that I can't solve, and hopefully you can help. I'll provide a little bit of background to this thing. This is maybe a bit of an unexpected title. It's called Transport in Soils. There's a lot of chemistry happening in soils, and I'll explain to you why we find that very relevant. Subtitle is Towards Clean Food. Clean, sustainable production of food requires clean soils and understanding the processes in soils. So that's what this is about. And that is because in the building, that beautiful building next door, that is also part of the faculty, where we are starting to establish real industry interactions between what chemistry and chemical engineering and materials engineering do and what industry needs. And we have, since I came here 9 months ago or so, been working on a strategy for that building, because we don't want just anybody in there. We want to really focus our research in there. And the research in there, we've decided we will focus on 3 pillars. One pillar is the one that all of you would have expected, I think, for a school of chemistry or for a chemically sort of oriented sort of like activity, is plastics and chemicals. The second one is alternative energy, because we do a lot of work in alternative energy, and alternative energy, of course, is a very important area to work in. And the third one is the one that I'll talk a little bit about today, is what we call clean food. Because we feel that the production, the sustainable production of clean food, high quality food, is a really important economical opportunity for Australia. Thinking about Asia, thinking about producing food in a sustainable manner and sell it into China. So clean food requires clean soils. That's where we're coming from. And there's a lot of chemistry involved in what happens in soils, and that's why I think it's an important area for us and for Monash to work on. You can think of things like fertilizers to keep the nutrient balance in soils, the nitrogen and the phosphorus and the potassium in balance, so that you don't take everything out to produce one enormous crop of something and then can't do it anymore. You need to make sure that these nutrients remain balanced. In Australia, in a dry country, there is a problem with salt accumulating in soils, called salinity or salinization, or sodicity, calcium sort of like getting bound to soils. Pesticides and pesticide residues. I mean, you can't have clean food with pesticide residues, and that's a real problem. And things that are even more exciting, called neopollutants, all the silver particles that we put in bandages these days, right? The silver colloid particles, or the nanoplastics, microplastics that we put in facial scrubs and things like that. They all end up in the environment, and ultimately in the soil, and ultimately in the product. So that stops you from producing clean food. I want to concentrate on pesticides now, but just an example. I could have picked all 4 of those. I hope that gives you a bit of a context. And pesticide residues are an emerging and serious problem in Australia, and that's partly due, and I'll explain why, because of the fact that we are Australia. We are dry, and there's not a lot of precipitation, and there's a net evaporation, and that's why the problems are bigger here than in the rest of the world. This is a very grotty little slide that shows, and I only want you to look at this. This is a Grain Research and Development Corporation, a really big project with hundreds of scientists involved from 5 different over 5 years done. It's very difficult to read this one, but this says like they do samples over, it says here like 40 grain cropping paddocks, really big ones, really important ones all over Australia. A lot of them in the west, of course, where the grain belt is, as all of you know, but also in New South Wales, also in Victoria. This is what they measure. This is measured in the top 10 centimeters of these paddocks. This is measured average over the 10 to 30, a bit deeper down. The most favorite and the most popular pesticide, herbicide, is glyphosate. As you may even know, that you use it at home. Don't. I mean, it's called Roundup. Glyphosate and its metabolite, AMPA, don't worry about its chemistry, those two you find in all the sampled fields. Right? They apply it year after year after year, and it accumulates and accumulates and accumulates. That's a real problem. And this glyphosate, this most popular one, is not the only one. I mean, there's lots more. So you've got to be very careful. If we next door start claiming that we know how to do chemistry to produce clean food, you've got to deal with this one, right? And that's where I need your help, I think. Soils are very complex, porous production systems. That's how I like to look at them. There is reactive flow happening, if you want some scientific terms. Reactive flows in porous media. The rain trickles through, does things, dissolves things, take things out of the soil complex. I mean, that's what's happening. It looks very much like chromatography. And I'm sure that some of you know all the difficult differential equations that have to do with chromatography, because chromatography was actually developed in the 60s or so, the theory around it, because of all the first nuclear tests that started happening and people getting worried about what happened to all these radionuclides raining out and how did they move through soil. So there's a wealth of 60s stuff that I personally don't understand because I'm not a mathematician, but that describes this sort of thing. And soils are mixed components of oxide minerals, iron, silicon, aluminium oxide, clays, humic substances, and then there's this funny thing, there's water there, or there's a soil solution there, right, in equilibrium with these particles, and there's a soil gas phase. And the Australian situation is very special because it's very dry here, as you well know. We've got too little rainfall, and compared to Europe, where you have a net downflux of liquid through the soil, here you get a net uprising, and therefore all these salinity and all sorts of problems start to happen. My statement would be, we need to be able to really make sense out of this, we need to be able to better measure, predict, and model what's happening in these soils. And what's happening in these soils are the interactions, the transport, the accumulation, the biouptake of components in the soil. And that's very true for agricultural production land. And today I want to make the point that it's very important for these soils, for these big production paddocks that provide food for a big chunk of the world, make sure that we don't mess it up by all these pesticide residues. So a strategy statement, and we can talk about it. I think there is a real opportunity for interdisciplinary teamwork. I mean, physical chemists, and I talk a little about it, can measure stuff that happens in these soils, but they can't possibly put it in a context. You need applied mathematics, is my view, to put it in a context, to actually predict what's happening. So better predictions and modeling would provide guidance for experiments, would then lead to better experimental results, and would then lead to better models, and would lead to strategies to actually really deliver on that statement that you want to produce clean food in this beautiful country of ours, right? More sustainable agriculture, cleaner food. And this is the system, and I'm sort of stealing a picture from Sjoerd van der Zee. I mean, I should have introduced him to you when I put up my first title slide. I mean, I do this work with Tony Petty, who has been in the school for a long time, who's a real expert on soils and sustainable production, chemistry that happens in soils. I'm interested in that space, and Sjoerd van der Zee is our adjunct professor from Wageningen University in the Netherlands, and they are really leading the world when it comes to soils and soil chemistry. But they're in a wet part of the world, so the things that he sees here are very different from what he's used to. Sjoerd would be a good guy to be here today because he is a physical chemist and he is really interested in and quite good at, in my view, in applied mathematics. So he would be a much better person to talk to you guys, explain what we really need than I am. But I'm just painting the picture, and Sjoerd will be here soon because he's an adjunct and he spends a fair bit of his time here in Adelaide, in Australia. So this is the sort of system that we're looking at. I mean, you've got the crop growing, the plants, the grass. You've got what soil scientists call the root zone. It's a fairly narrow 5 centimeter sort of layer, 10 centimeter layer where the roots are. Then you've got soil, and then you've got a water table. And the processes that are happening there, of course, depend on how much evaporation takes place through the crop or through the sunshine, how much precipitation happens through rain. The processes that are happening here, roots taking it out, and then some of it filters through to the groundwater, or in the Australian situation, quite a bit of that is capillary, in a capillary rise sort of way, connected to this. And you can see immediately, I think, in a country like Australia, as soon as you start irrigating, you never do that with distilled water, you know, but you do that with water that has salt in it and stuff in it, you accumulate. The more you irrigate, the more you accumulate, the more problems you get with salt accumulation in this layer, and the more problems you get to grow food, to grow crop. But this is sort of starting to smell like mathematics, and I mean, this is as far as I can get, and I'm really sort of like helpless here. But what most people do, what Sjoerd does as well if he works with us, I mean, you start with this one-dimensional convection dispersion equation thing, right? And this is, I'm sure you guys understand this. I mean, this is the hydrodynamic dispersion coefficient. There's a breakdown assumed here, and that's a weakness of this whole thing. You assume that the stuff that you apply to a crop, to land, is decomposed in a first order kinetic sort of way. That's an oversimplification that sticks in here already. Then there is an interaction between your herbicide, in this particular case in your soil particles. You stick in what they call an adsorption isotherm. And as a physical chemist, I've got great problems with this one, because this is what I call a Freundlich isotherm, and it's just a fitted thing. It doesn't mean anything about what's actually happening. But then if you do that, and I sound much more critical than I want to be, because this is already quite an achievement, doing that you can actually start to work out profiles of things in soils, and you can then start telling farmers and food producers what actually the risks are that they're taking. And I don't think Kate will give me the time to talk about this much, but what you can, 3 minutes, 4 minutes. If you do the sort of like mathematics that I was just showing, that Sjoerd's really good at, and there's published a lot about, you can calculate these sort of like profiles going into the depth and looking at what the concentration or the effective concentration of a component is. This one is assuming that there is no transformation, so there is no biological activity to break down the pesticide, which is a horrible situation to be in, of course, and this one assumes that there is decomposition happening. What you see is, and I'm sure you understand this, I mean, you see these long tails happening if the thing moves through the soil profile. And the other thing that you see, which is a really important one, I'll talk about it in a minute, is that this percentage here is the percentage of the herbicide in this case that is present in the solution. So there's less there, and there's less there in solution. And that's really important, because people assume that only the herbicide that is in solution gets transported and gets broken down. So if you look at the breakdown that is happening, and you introduce it through what's called the Damköhler number, it doesn't really matter, but that sort of expresses in dimensionless properties how quickly a component breaks down. You see that it slows down a lot. The movement of the wave itself slows down a lot, and you see even a stronger trend. There's far less in solution all the time, so there's far less to break down, so it stays there much longer. This is just a very sort of like quantitative explanation of how you look at these things, but at least these profiles that we're really interested in, and I think interested in the more realistic conditions, how they can tell you what the risks are and what the concentrations are, what you can do in order to avoid problems. I'm well out of my depth here, of course, so I want to go back to where I feel a little bit more at ease. So one of the things that you assume here, and we don't know anything about it, and it is a real concern, right? I mean, we don't know how these solutes, how these herbicides interact with the solid components of a soil. We assume things, we got to measure them. There's ion exchange happening, of course, because I mean there's sodium and calcium, and these things are charged, they can exchange against the sodium and the calcium. That's one. The other one is a much more important one in my mind, is adsorption. And I said, like, the best thing you see in the literature is a Freundlich isotherm. It's just a fitted thing, and you fit a relation and then you use it in your modeling exercise. You can do a hell of a lot better than that, though. And there is a lot of isotherms that you could use, and which one do you pick and why do you pick one, and if you pick one, how can you measure them? That's sort of like the area that we are really interested in. The most simple one is what's called the Henry one, is a linear relation between adsorbed amount and concentration in solution. I've shown you the Freundlich one, which is basically a fitted one. Those two are the much more interesting ones, because there's a physical model, a chemical thermodynamic model behind them, the Langmuir isotherm, that says like the adsorbed amount is a constant with a free energy in it times the concentration, and this, the Frumkin isotherm, is a advancement on the Langmuir, where you assume that the molecules that are adsorbed interact laterally. They attract each other or they repel each other, and therefore the isotherms can get these sigmoidal sort of like shapes. What I'm trying to say is, in order to know what you want want to measure to feed into the models, you need to really sort of like start to work through those sort of like consequences and design your experiments accordingly. I'm almost finished. Can I have 2 more seconds? Because what happens is, and that is very important, right? Why does this guy talk about adsorption isotherms if you talk about the big picture? Well, this is the reason why. We assume, and we're not even sure about that, that if a certain concentration leads to a certain point on an adsorption isotherm, part of it is adsorbed onto the soil particles. And it is assumed that there is no decomposition activity happening in the adsorbed phase. So bacteria can't really break it down, oxygen can't really oxidize it. So it's only in the solution. So the form, the shape of this thing is really important. So you need to do the measurements, you need to really talk and think through how that works out on the overall performance of the system. So the challenge is, I think, by a combination of sophisticated modeling and smart physical chemical experiments of the nature that I just showed you before, adsorption, breakdown, is it possible, question mark, to accurately predict the accumulation of residues in production soils and the bioavailability of these residues? And ultimately, is it possible to, by understanding this, design better, more specific, more targeted crop protection agents like fertilizers, or in this particular case, pesticides? And I think that's where physical chemists need soil chemists, need applied mathematicians. That's sort of the story that I wanted to give you.
Thank you very much.